Here we're given a triangle with a smaller triangle superimposed over it, and the lengths of various different portions of these triangles. And we can also see that side AB and side DE are parallel, and side BC and EF are also parallel. So given this information, the first part asks us to prove that triangle DEF is similar to triangle ABC. I'll do this by using the tried and trusted strategy earlier mentioned. Just prove that two angles are equal for the two triangles. And since we know that two of the three sides are parallel, this will be pretty easy to do. First, we can look at these two angles, meaning angle EDF and angle BAC, which will be equal because these two angles are corresponding angles between two parallel lines. And we can do the same for this angle and this angle, so angle EFD and angle BCA, for the exact same reason, which is that the two angles are corresponding angles that fall between parallel lines. Therefore, we've proven that two angles are equal, and that concludes that the two triangles are similar. Then for part B, it asks, what is the value of x? Going back to the diagram, it's asking, what is the length of this side? Since we have so many numbers given, we can just use the proportionality of the various sides. So I'll go for the ratio of x over 16 is equal to the ratio of this side over this side, meaning 10 over 4 plus 10 plus 6, which will just come down to 10 over 20 or half. Then rearrange for x, which would be x is equal to 16 times half, which is just a value of 8. And that's the value of x. Then moving on to the second proof of the section, and that's the proof of the statement that if the corresponding sides of two triangles are in proportion, so the second condition required for similarity, then this implies that they are similar. So if the corresponding sides of two triangles are in proportion, then it automatically implies that all interior angles are also equal, which is the second condition for similarity. So that's what we need to prove. Given the fact that the sides are proportional, this would imply that the triangles are equiangular. This is how we would prove it. Given a triangle ABC and a triangle DEF, with all three sides being in proportion, in other words, the ratio AB over DE would be equal to the ratio CB over FE and also AC over DF. And given these facts, we therefore need to prove that the corresponding interior angles are also equal, meaning A hat is equal to D hat, B hat is equal to E hat, and C hat is equal to F hat. The first step is draw a line XY in this larger triangle so that the length of the side DX is equal to AC and length DY is equal to AB. Here's what this looks like. So I've added this line XY so that DX is equal to AC and DY is equal to AB. So I'll start by noting the information we've already been told in the question, which is that AC over DF is equal to AB over DE. Then I'll replace AC and AB with DX and DY, which I can do because that's how I defined DX and DY. So since the ratio of DX over DF is equal to DY over DE, we can draw on the proportion theorem again, or rather the converse proportion theorem, because the normal proportion theorem said that if we draw a line parallel to the third side, then it divides the other two sides in the same proportion. So the converse proportion theorem would say that a line such as xy that divides two sides in the same proportion as demonstrated here would be parallel to the third side, meaning xy is parallel to FE. Since xy divides DF and DE in the same proportion. Then, since we know that these two lines are parallel, we know that these corresponding angles would be equal to each other. So f hat is equal to dxy and e hat is equal to dyx, both due to being corresponding angles between parallel lines. And since we know that the triangles dyx and DEF have two angles in common, meaning this angle and this angle, that's enough to say that the two triangles are similar. And since they're similar, we can equate various ratios. So one of these is xy over FE would be equal to dx over df. And since I drew dx to be equal to AC, I can substitute AC over here, giving equals to AC over df. So I have the ratio AC over df. So we've seen this ratio AC over df before, and that was as told earlier in the question. I'll go back to the question just to show you. There. So we had AC over df, and from the information given in the question, we can equate this to CB over FE, like shown over here. So from this long exercise with all these fractions over here, we started off with xy over FE, and we ended up at CB over FE. And since they have equal denominators, we can also say that the two numerators are equal, meaning xy is equal to CB. And this is a useful piece of information because this enables us to show that triangles DYX and triangle ABC are congruent. I'll go back to the diagram. So we constructed DX to be equal to AC and we constructed DY to be equal to AB, and we proved that XY is equal to CB. Therefore, we can say that triangle DYX and ABC are exactly the same since they have three sides of the same lengths. So DYX and ABC are congruent. And with that step, we can finally prove that the two triangles ABC and DEF, which we were told in the question have the three sides in proportion, are also equiangular, since we know that ABC and DYX are exactly the same triangle and DYX is similar to DEF. So by extension, triangle ABC is similar to triangle DEF and consists of the same three corresponding angles. And that concludes the second proof. So we've proved that given two triangles for which any of the two similarity conditions are met, automatically implies that the other has also been met. Therefore, to show that two triangles are similar, we just need to show that one of the conditions has been met. Then let's wrap up the similarity of triangles section with an example. In the diagram given, the points A, C, D, and G all lie along a circle's circumference. Then there's a lot of things that haven't been mentioned in the question, but I'll just tell you so you have a good understanding of how this diagram came about. So originally you have the circle with the points A, C, and G, and A is directly connected to G and G is directly connected to C. Then what is done is this point mentioned here, that GF is drawn so that GF is equal to 2 times AG, which is why you have this point F over here. Then this point F is connected to the point C, which causes it to cut the circle at a point that's labeled D. Then the point A is connected to this point D, and the point where it cuts the line CG from earlier is labeled as point B. And then comes the second piece of information mentioned in the question, which is that this line ABD is extended up to a point E so that the line EF is parallel to CG. So that's basically the bunch of things that happened to end up at this diagram. So given this whole setup, the question consists of various parts of everyone's favorite type of questions, which is proofs. The first of which is prove that AB over AE is equal to 1 over 3. So to prove this, the first thing I'll draw upon is the fact that the lines CG and EF are parallel. And since we have the triangle AEF and the side CG is drawn that's parallel to this third side EF, using the proportion theorem, that would mean that the line CG splits the line AE and AF to the same proportions. Then we can rewrite this AG over AF function by expanding AF to AG plus GF, since AF is made up of the portions AG and GF. Then, as mentioned in the question, GF is equal to double the length of AG, so we can substitute GF with 2AG. Then all these AGs would cancel off, leaving just 1 over 1 plus 2. Giving 1 over 3. And that proves the question. And for part B, we need to prove that triangle ADF is similar to triangle CGF, meaning this triangle and this triangle. So I'll go for the same strategy as I did previously, which is proving they're similar by showing that they have two angles in common. So for triangle ADF and CGF, the most obvious option is this angle, because it's common to both the triangles. So for triangle ADF, that would be angle AFD, and for triangle CGF, that would be angle CFG. So we know one angle is equal. Then for the second angle, I'll actually draw upon one of the circle properties I covered in the revision section, more specifically the second one. Let's look at the diagram. We're looking at this triangle and this triangle. And the circle property I'm talking about is the fact that the same arc will subtend the same angles at the circumference. Therefore, this angle and this angle are both equal. So A hat is equal to C hat, since they're both subtended to the circumference by the arc DG. And since we've shown that they have two angles in common, that proves that triangle ADF and triangle CGF are similar. And for the final part of this question, we need to prove that DF times CF is equal to 6AG squared. And to get this, I'll first draw upon the result from the previous part, which was that triangles ADF and triangles CGF are similar. And based on this, the ratio of DF over AF is proportional to GF over CF. Then cross multiplying gives DF times CF is equal to AF times GF. Then we can just replace these two terms with something in terms of AG. Let's look at the diagram again. So we want to rewrite AF and GF in terms of AG. So GF is pretty simple. We already know it's equal to 2AG. And then AF would be 3 times AG, since that's 1 AG and that's 2 AG. So the total is 3 AG. Then you just multiply this out and that gives 6 AG squared as required. And that concludes the similarity section of the topic. And then we can now look at the final section of Euclidean geometry, and that is the Pythagorean theorem.